Welcome back. We've already explored the dot product through a formula, so in this video we're going to describe the dot product more geometrically. We'll firstly introduce a geometric formula for the dot product, and we'll prove where the formula comes from. We'll follow that up with some examples on how to use this formula. So if we're talking about a geometric approach, let's draw two random vectors on a number plane. Remember, these vectors will have both magnitude and direction. The magnitude will be the length of the vector, denoted by this for vector A and this for vector B. The neat thing about this is that we actually have a formula for the dot product which relates what we've drawn up. This is the formula. The left-hand side is the dot product that we defined last video. These parts are the magnitudes of A and B respectively, and the theta here is the angle between the two vectors. So it's this angle on our plane. Note the importance of the word tail. If instead our situation looked like this, the angle here would not be theta, because that's the angle between vector A's head and vector B's tail. Our actual theta would be this. Now, like anything in life, it's always nice to know where things come from. So let's prove this formula. Vector proofs can be a little tricky, so we'll break this one down by first drawing up the triangle, let's call it OAB, where O is just the origin. We'll then apply the cosine rule in this triangle. Now, what are the lengths of each side of our triangle? Well, the length of OA is just the magnitude of vector A, which is this. Similarly, the length of OB is the magnitude of vector B. What about BA? Well, BA, with the direction from vertex B to vertex A, is the same as the vector A minus B. So the length of the side BA is just the magnitude of the vector A minus B, aka this. Note you could instead take the vector B minus A and the proof would be pretty much identical. So we have three side lengths of a triangle and an angle. That's exactly what we need for the cosine rule. If we pull up the cosine rule for some general side lengths x, y, and z, then we can substitute in our side lengths. What I mean is letting x, y, and z be these values. And of course, our theta can stay as theta as it is in the triangle OAB. Using the cosine rule, this is the expression we arrive at. Recall that the magnitude of a vector A is the square root of each entry squared, like so. Notice in our equation we have this quantity squared, and these other similar terms. You can see the terms match up. Let's now substitute these into our equation. We've left this part of our equation untouched because notice it appears in our final formula. Now we can expand these perfect squares quite simply to arrive at this. There are plenty of like terms that cancel out on either side, so we can simplify to this. I hope you can sense we're very close to the formula we're trying to prove. Dividing by -2, and then the left-hand side is precisely what we defined the dot product between vectors A and B to be. So we're there. This is our formula for the dot product from a more geometric view. This formula tells us that the dot product between A and B is the magnitude of the vectors and the cosine of the angle between them all multiplied together. You may be wondering what sort of questions will involve this formula, so let's look to a couple of examples now. Here's the first question. We are given the magnitude of two vectors A and B and the angle between them. We are asked to find the dot product between them. Geometrically, this situation might look something like this. Whenever you are given the angle between two vectors, you know there's a good chance this formula will be involved. In fact, in this case, we can just substitute straight into our formula. That is, the dot product of A and B is 4 times 5 times the cos of 120 degrees. The cosine of 120 is -1/2, recognizing that the related angle is 60 degrees and we are in the second quadrant. I suggest a bit of trigonometry revision if that isn't straight away clear. This leaves our final result as a -10. I hope you'll agree that this formula was extremely helpful here, because we wouldn't have been able to calculate the dot product from our definition last video, seeing as we didn't know the entries of each vector. Another quick example is this. This time we are showing an identity. If we look to the plane, just take some random vector A in this direction. If we pull up our fresh dot product formula, and this time let B equal to A, we have this. But theta in this case is actually 0, because the angle between A and A is 0. They are both the same vector, so they have an identical direction. Subbing theta as 0 into our formula, and knowing that the cosine of 0 is 1, we achieve the identity we were asked to show. A nice little result to keep in the back of your mind. With those two examples, let's round off this video. We were introduced to a new formula for the dot product, which is generally referred to as the geometric description of the dot product. The example showed what sort of questions may be asked. The formula can actually be used to help us with another application. We'll cover that soon. I'll see you for now.